grounding electrode system described is generally reasonable for a facility of this type and size. However, a few clarifications and recommendations should be noted. The distance between the transformer frame ground electrode and the built-in grounding electrode system should be as short as possible to minimize impedance and potential differences. Less than 20 meters is acceptable, but shorter is preferable. While a ground ring around the building is not strictly necessary, it can provide additional protection and redundancy. It is recommended to consider installing a ground ring if feasible. The concept of single-point grounding is generally not recommended for high-frequency applications due to the potential for ground loot and noise. It is recommended to separate safety grounding, the equipment grounding conductor, from signal grounding, the reference potential connections. To prevent ground loops when testing equipment, it is recommended to use isolation transformers or ground isolation probes, rather than swapping feeding cords. For equipment operating at megahertz range, it is important to ensure that the grounding system has low impedance at these frequencies. This may require special considerations, such as using copper grounding rods or straps with large cross-sectional areas. Consider installing surge protection devices on all incoming power lines and communication lines to protect against transient overvoltages. Implement appropriate electromagnetic interference shielding measures, such as shielded cables and enclosures to prevent interference with sensitive electronic equipment. Regularly test and maintain the grounding system to ensure its integrity and functionality. Overall, the grounding scheme described provides a reasonable foundation for a telecommunication equipment manufacturing facility. However, it is advisable to seek professional engineering review and assessment based on the specific details and requirements of the facility. Grounding is a critical aspect of electrical system design, particularly in facilities housing sensitive electronic equipment. A well-designed grounding system ensures safety, minimizes electrical noise, and protects equipment from damage due to faults or surges. Let's delve into the key components and considerations for effective grounding in a telecommunications equipment manufacturing plant. Firstly, the grounding electrode system serves as the foundation for the entire grounding network. This system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes, that are bonded together to form a low-impedance connection to the earth. The primary purpose of the grounding electrode system is to provide a path for fault current to flow back to the source, thereby tripping the overcurrent protective devices and disconnecting the faulted circuit. Secondly, the grounding electrode system should comply with the requirements of the National Electrical Code, specifically Article 250. The NEC specifies the minimum size and type of grounding electrodes, as well as the bonding requirements for connecting them together. The overall resistance of the grounding electrode system should be low, ideally less than 25 ohms, to ensure effective fault current dissipation. A lower resistance value is generally desirable, especially in facilities with sensitive electronic equipment. Thirdly, the grounding electrode system should be connected to the service equipment grounding bus, which serves as the central point for all grounding connections in the facility. The service equipment grounding bus should be bonded to the neutral conductor of the electrical service, as well as to the building's structural steel and metallic piping systems. This bonding ensures that all metallic parts of the building are at the same potential, minimizing the risk of electrical shock. A ground ring, which is a continuous conductor encircling the building, can provide additional protection and redundancy. The ground ring should be buried at a depth of at least 2.5 feet and bonded to the grounding electrode system at multiple points. While a ground ring is not strictly required by the NEC, it is often recommended for facilities with sensitive electronic equipment. Equipment grounding refers to the practice of connecting the non-current carrying metal parts of electrical equipment to the grounding system. This includes equipment enclosures, chassis, and raceways. The purpose of equipment grounding is to provide a low impedance path for fault current to flow back to the source, thereby protecting personnel from electrical shock. The equipment grounding conductor, or equipment grounding conductor, is the conductor used to connect the equipment enclosure to the grounding system. The equipment grounding conductor can be a wire, a raceway, or a combination of both. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. The equipment grounding conductor should be installed in the same raceway or cable as the circuit conductors. Single-point grounding, also known as star grounding, is a grounding topology in which all equipment grounding conductors are connected to a single point, typically the service equipment grounding bus. The idea behind single-point grounding is to minimize ground loops, which can cause noise and interference in electronic equipment. However, single-point grounding is not always the best solution, especially in high-frequency applications. In high-frequency circuits, the impedance of the equipment grounding conductors can become significant, leading to ground bounce and other problems. A ground loop is a closed loop of conductive material that is connected to ground at multiple points. Ground loops can occur when there are multiple paths for current to flow back to the source, such as through the equipment grounding conductors and the building's structural steel. Ground loops can cause noise and interference in electronic equipment, as well as create a safety hazard. To prevent ground loops, it is important to minimize the number of ground connections and to ensure that all ground connections are made with low impedance conductors. Isolation transformers can be used to break ground loops by isolating the equipment from the power source. Isolation transformers have separate primary and secondary windings with no direct electrical connection between them. This prevents current from flowing between the primary and secondary circuits, thereby eliminating the ground loop. Another way to prevent ground loops is to use ground isolation probes. Ground isolation probes are devices that are inserted into the ground connection to break the ground loop. These probes typically use a high-frequency transformer to isolate the equipment from the ground. High-frequency grounding requires special considerations due to the skin effect, which causes high-frequency currents to flow on the surface of conductors. This means that the impedance of the equipment grounding conductors can be significantly higher at high frequencies than at low frequencies. To minimize impedance at high frequencies, it is important to use wide, flat conductors, such as copper straps, rather than round wires. These straps have a larger surface area, which reduces the skin effect. It is also important to keep the equipment grounding conductors as short as possible. Surge protection devices, or surge protective devices, are devices that protect electrical equipment from transient overvoltages, such as those caused by lightning strikes or power surges. Surge protection devices work by diverting the surge current to ground, thereby preventing it from damaging the equipment. Surge protection devices should be installed on all incoming power lines and communication lines. The surge protection devices should be selected based on the voltage and current rating of the circuit being protected. EMI shielding is the practice of reducing electromagnetic interference, or EMI, by blocking or absorbing electromagnetic radiation. EMI can be caused by a variety of sources, such as radio transmitters, cell phones, and electrical equipment. EMI can interfere with the operation of electronic equipment, causing it to malfunction or produce incorrect results. EMI shielding can be achieved by using shielded cables, enclosures, and filters. Shielded cables have a conductive layer that surrounds the conductors, preventing electromagnetic radiation from escaping or entering the cable. Shielded enclosures are metal boxes that enclose the equipment, providing a barrier against electromagnetic radiation. EMI filters are devices that block or attenuate electromagnetic radiation at certain frequencies. Regular testing and maintenance are essential to ensure that the grounding system is functioning properly. The grounding system should be visually inspected on a regular basis to check for loose connections, corrosion, and other damage. The resistance of the grounding electrode system should be measured periodically to ensure that it is within acceptable limits. The surge protection devices should be tested regularly to ensure that they are functioning properly. In summary, a well-designed and maintained grounding system is critical for the safe and reliable operation of a telecommunications equipment manufacturing plant. The grounding system should comply with the requirements of the National Electrical Code and should be designed to minimize ground loops and EMI. Regular testing and maintenance are essential to ensure that the grounding system is functioning properly. Firstly, ensure compliance with local electrical codes and regulations. Secondly, implement a comprehensive grounding system design. Thirdly, use appropriate grounding conductors and connectors. Fourthly, minimize ground loop potential. Fifthly, provide adequate surge protection. Sixthly, implement effective EMI shielding. Seventhly, establish a regular inspection and maintenance program. Eighthly, consider using isolated ground receptacles. Ninthly, properly bond all metallic components. Tenthly, document the grounding system design and modifications. The goal is to ensure a safe, reliable, and interference-free operating environment for the sensitive telecommunications equipment.